Hello everybody and welcome to this video. Now we're going to look at some examples of power and energy to kind of solidify some of the concepts that we just talked about. So looking at this first example, it's saying that we have an energy source that is forcing a constant current of 2 amps for 10 seconds to flow through a light bulb. If 2.3 kilojoules is given off in the form of light and heat energy, calculate the voltage drop across the bulb. So obviously before I start, I'd like you guys to give it a try and try to see if you can solve it for yourself. I'd like you to pause the video and do so. Alright, so now I'm going to go ahead and do the solution then. So the first thing I would do on a test or anything like that if I want to solve this problem is to write out what I'm given. So the first thing I'll probably write is that we have a current of 2 amps. Let me write this in white. We have a current of, let's write it over here, I is equal to 2 amps. So those are the givens. Kind of going out with a systematic way to solve these problems. So 2 amps, and the time that's going by, the delta t, is 10 seconds. And what else do we know? We know that it's going to a light bulb, and there's a power dissipation because it's saying that it's given off, this power is given off in the form of light and heat, and then that would just be a positive power, right? Because you have some positive current and positive voltage, and I'll go into the details of that in a minute. That is 2.3 kilojoules. In kilo, hopefully you know by now, it's just 10 to the 3 or 1,000. I would suggest that you guys get familiar with the prefixes for SI units, for System International units, for example meter and all that stuff, and getting comfortable with the prefixes. Like mostly for this class we'll be using kilo, micro, excuse me. I believe sometimes we'll get let's see, mega or pico, and this would be 10 to the 3, 10 to the 6, 10 to the negative 6, and of course milli, I forgot that, that's 10 to the minus 3, and pico I believe is 10 to the negative 12. And let's see what else. Nano would be another one. Nano is 10 to the negative 9, or 1 billionth. So keeping that aside then, let's keep that over there just to be familiar with those. The other thing we got to worry about now is, so we wrote down what we're given, and let's see what is, okay, we got that, light and heat. What we need to find though is the voltage drop across the element. So I'll write V sub R for or V sub L for load. Okay, so let's now draw a diagram to kind of see what's going on here. So what I'm going to do is remember that I have some voltage source, which I'm not going to draw that, I'm just going to draw the element. It's a light bulb, but remember it's giving off power, so I'm going to treat it as if it is just a resistor. It's my approximation to how this thing is going to behave. So there's going to be some voltage drop across it, assuming positive or passive sign convention. There's going to be some current going in here, which we do know. So that's known. The voltage is not known. The power is known. 0.3 kilojoules. Now, this whole thing was just to write down what we know and kind of set the problem up. But now we got to think about how to solve the problem. So the first thing is, we got to think about what kind of relationships relate current, voltage, power, and time to each other. So the first thing I'm going to do is write down what I know about current. Current is coulombs per second, so the amount of charge per second. Or since I'm not doing any calculus or differential equations right now, I can write this as delta Q per delta T, or T because we're assuming that time starts at 0, so delta T would just be T minus 0 or T. So I'll just leave it like that. And let's see, if I want to find the total charge, I'll just say and multiply. As a matter of fact, in this case we would probably need to use delta T to say how much time has passed, is equal to delta Q. So what we're saying right now is, I just rewrote this in a way to say that since we know I, and we know the amount of time passed, we can find the charge. So what does that mean? It's saying that the current is flowing through this for 10 seconds. 10 seconds of the same current flowing in. So what does that mean? That means that charges are going through this element right now, and as a result, there's energy being released as form of heat and radiation, or electromagnetic radiation, which is light. So I'm going to plug those guys in, and I get 2 amps times the change in time, so 10 seconds is equal to, what's that? That's 2 coulombs per second. That's what 1 ampere is. Remember, 1 ampere is 1 coulomb per 1 second. Multiply by 10 seconds, so seconds cancel out, and it's a good habit to start writing units down so you don't get any mistakes. 20 coulombs is the amount of charge that passed through this whole thing for 10 seconds and a current of 2 amps. So that is my delta Q. That's one thing to remember here. I wouldn't circle it because that's not the final answer, but just to remember it. So that's one thing. So the other thing, we need to somehow relate let's see, power and let's see, time or charge or current. Let's see what we can do. Power is given by dW dt, which we found out was just voltage times current. And let's see, what else do we know? We know that let's see, if you want to find the voltage, we could either do power being power over I is equal to voltage, or and let's see if that works. I'm gonna go ahead and plug these in and see what happens. We get 2.3 whoops 2.3 kilowatts, I believe that's what it was. Kilojoules, I'm sorry. Let's see, did something go up here? Oh, I made a mistake here. That's what that was. The units are not right. We're not given power. We're given units of energy. So what we know, that's energy. So I'll just go ahead and label that as let's see, W. That's what we know, not power. Power has watts, not joules, meaning energy per second. So that's what was giving us confusion here. So let me clear these out. Even if they're true, there's another step for us. So let's see, what do we know about voltage? Well, voltage is it is joules per coulomb, so the units, so energy per charge. So what that's going to give us is the change in energy, which is 2.3 kilojoules per the charge that we found was 20 coulombs. So that's the same thing as 2.3 times 10 to the 3 joules over 20 coulombs. Joules per coulomb, which is just volts. And I'm going to plug this into my calculator. And what we get is 2.3 e to the 3 over 20. We end up at 115 joules. Which makes sense because that is pretty typical for light bulbs. Around 115 to 120 or so is pretty reasonable. So that's that problem, and let's go on to another problem. Okay, in this example, it's a pretty elementary example, and it says to move charge Q from point A to point B requires negative 30 joules. Find the voltage drop if A, you have a charge of 6 coulombs, and B, if you have a charge of negative 3 coulombs. And remember, charges come in positives and negatives, so in two different varieties. So first I want to think about the charge, whatever that is inside of this is a total charge. I need to move it from point A to point B, and that's going to require some energy. And they're saying that it's going to be a negative 30 joule energy, and that negative just depends on as a matter of who's losing that energy. So if it's negative, that means in this context something, maybe conductor needs to be losing energy to give this particle, to give this charge energy to be able to move through to the desired point here, point B. So here I'm just going to think about A, which says there's 6 coulombs. So for part A, we have 6 coulombs of charge, and let's see, we have to find the voltage drop if we have a energy of negative 30 joules. Well, we know that voltage is the work done over or the instantaneous work done over the instantaneous amount of charge. So let's see, that would equal negative 30 joules over 6 coulombs, which should just be negative 5 volts. So it will take a negative 5 volt supply to, and that negative is just as a matter of arrangement, which should the polarity of it, how should it be arranged to supply that amount of energy. And for part B, we want to find the voltage drop if you have a charge of negative 3 coulombs and a work of negative 30 joules. So what I'm going to do is draw the charges again. Negative 3 coulombs. We got to move these guys from A to B, and it's going to require some energy, and the voltage drop needed to do that energy is going to be negative 30 joules over negative 3 coulombs. Negatives cancel out. 30 over 3 is 10, and joules are over coulomb are volts. So we need 10 volts to move negative 3 coulombs of electrons from some point A to some point B. So that is that problem. Okay, in this example we have what is asked is to find the power delivered to an element at the point or at the time 3 is equal to 3 milliseconds if the current entering the positive terminal is given by this function over here, and the voltage across is given by A being voltage is equal to 3 times the current, and at B voltage being 3 times the rate of change of the current at t is equal to 3 milliseconds. So the first thing is I'm just gonna draw the element and just try to think about it. So you have some element here, and you have some voltage drop across it. The voltage drop, and let's see, so that's the voltage drop, and you have some current going, it says from the positive terminal, so that clarifies that the element is not sourcing the current, it's actually receiving the current and it's absorbing it. So we know that the power using passive sign convention is going to be positive, meaning it's getting dissipated. So recall that power is instantaneous power, meaning at any given point in time, if you multiply that particular current times that particular voltage, you get that particular power being consumed or absorbed or lost at that particular time. So let's go ahead and now and think about what is the voltage at let's write that down. 3 is equal to 3 milliseconds, which is 3 times 10 to the negative 3 seconds. And for part A, voltage will be 3 times whatever current is. So let's see, that's amps, so the units must be 3 volts per amps. So I'm just going to write it like that. If you're going to end up with volts, you're going to need to have volts per amps multiplied by 5 cosine of 60 pi t amps. So amps cancel out, you get volts, and you get volts is equal to the voltage is 15 cosine of 60 pi t volts. That is my voltage at from part A. So it's going to be, and my time is 3 milliseconds, so I'm going to plug that in, and I get voltage is 15 cosine of 60 pi multiplied by 3 times 10 to the negative 3 seconds volts, which should be, let's plug that into the calculator and make sure it's in radians, otherwise you're going to get a different weird answer. So it's 60 pi times 3 e to the negative 3 And what am I gonna get here? Let's see. I'm gonna get. I'm actually gonna do something here. I'm gonna keep the answer in a symbolic form here and not plug in answers, and do that at the end to kind of make things simpler. So we found the voltage, and let's keep that in that particular form. So I'm gonna keep it over here. Remember that we found the voltage for part A, and the current was already given, so I'm gonna plug let's see, I'm gonna multiply the current and voltage here, and I'm gonna get 5 cosine, that's the current, cosine of 60 pi t amps being multiplied by 15 cosine of 60 pi t volts. And what I end up getting is 5 times 15 should be, let's see, 75, and we have a cosine of the same argument, so we can say cosine squared of 60 pi t evaluated at t is equal to 3 milliseconds, which should be, now I can plug that in, and I'll get 60 pi times 3 times 10 to the negative 3 seconds. And now we can plug that into the calculator and see what we get here. And that's going to be our power that is consumed, because it's a positive power. So that means it's being absorbed and consumed for some reason, to do some work. So what we get here is we get 75 times cosine squared. Let's see here, putting this into the calculator, cosine 60 pi times 3e to the negative 3. Now let's make sure we square the right thing here. And I end up getting positive 53.47 watts. So that is for part A. That's how much power the object is using, dissipating away. And for part B now, the voltage is going to be 3 times the rate of change of the current. So rate of the change of the current, so we gotta look at the current, which is that right there, and the rate of change of current is going to be the rate of change of 5 times cosine of 60 pi t. And what that's going to be is, well, 5 is a constant with respect to time, so we're going to pull the 5 out and take the derivative of the cosine with all the argument inside of it. So that's going to be d dt of cosine, which is going to be negative sine of 60 pi t. And remember, chain rule, we have to take the derivative of the inside now, which is going to be 60 pi. And the final answer here for the current, the di dt, is going to be, let's see here, 60 here, so that's times 5, so that's negative 300 pi sine of 60 pi t. And let's see here, now we found that, so multiply by 3 to get the voltage. I'm going to multiply by 3 on both sides, and I'll end up getting 900, I believe. So let's see, right, so negative 900 pi times the sine of 60 pi t. So that is going to be our voltage. So now if you multiply the voltage and the current, that's going to give us the power that's being dissipated by that element. And we can see that the voltage obviously changed. So let's see here, di dt. We got to make sure we multiply by the right. We can't multiply by di dt, so I'm going to look at the current. I'm going to rewrite everything here. So the voltage for part B is negative 900 pi sine of 60 pi t, and the current initially was, I believe, 5. What was that? Cosine of 60 pi t, so cosine of 60 pi t, and the power is given by current times the voltage, which is equal to, in this case, negative 900 pi sine of 60 pi t multiplied by 5 cosine of 60 pi t. And that is going to give us negative 4,000. Let me double check. 4,500. But let's see. Yep, 4,500 pi. Now let's see. Did I do this right? I get a sine and a cosine, so it should be right now. Sine of, let me write this down. T is equal to 3 milliseconds. We got to evaluate that at 3 seconds. 3 milliseconds. So that's multiplied by. Let's take that out here. 3 times 10 to the negative 3 seconds. That multiplied by cosine of 60 pi times 3 times 10 to the negative 3 seconds. So I'm gonna do that in the calculator real quick and give you the answer. Okay, so what I ended up getting is negative 6,395.845, which we're gonna round up to, let's see here, negative 6.396, and we're going to say that is in kilowatts. Now you can see that it's a negative here, which means that the element, whatever it may be, it is supplying power in this particular moment. If the voltage is the power is depending on the rate of change of the current, we're going to get a sine function for the rate of change of the current, and that sine function has a negative behind it, and that negative is going to carry out and give us a negative power, which means that the element for option B, for part B, is going to be supplying power, meaning either the current or the voltage are going to be flipping in directions, making it a negative number. So what I'm saying is this: if it was positive, like the initially, that's what we would have, like the initial case in part A. But if in part B, either the current has flipped directions or gone from here to going this way, or the voltage has flipped polarity, instead of going this way, it's now going this way. It could be either of the two, but not both, because if it was both, they would both be negatives and cancel each other out. Okay, looking at another problem, now we have a more practical one, where we're dealing with kind of like watt hours, or the energy spent. So this one is saying, how much energy does a 100-watt electric bulb consume in 2 hours? So we can see that the time given is 2 hours, and the power is given as 100 watts. And we have to remember that is 100 joules per second, or units of energy per second. And we're given time, so that you can see that here, if we convert this into seconds, we can find the total energy. So let's write the power relationship, which is amount of work done per time. So we want to find the energy, so we're going to solve for work. Multiply both sides by T. Should put it this way. So I'm going to get work is equal to P times T, and let's see, that is going to be equal to the power, which is 100 watts, or joules per coulomb, or joules per second, I'm sorry, joules per second, multiplied by the total time, which is 2 hours, and we got to convert that into the correct units of seconds, otherwise we'll be in non-standard units. So that'll be, for 1 hour you have 60 minutes. Per 1 minute you have 60 seconds. Let's see, hours cancel out, minutes cancel out, and you end up with seconds, and that is what we need. So let's see, well, after that though, seconds cancel out and you get joules. So I'm gonna write 100 joules multiplied by 2 times 60 times 60. Well, 60 times 60 is 3,600, and 2 times that is 7,200, and that is seconds, but I already canceled that out, or I can just write it here. So that cancels out, and you get another 100 here, multiplied by that. So you're gonna get, let's see, you're gonna end up getting 720,000. Let's see here. And if you want to convert that into watt hours, you gotta remember that 1 watt hour is going to be 3600 joules, and this was in joules. I forgot to do that. So if I divide this out, right, so the reason you want to convert it to watt hours is because joules, it's a huge number of joules, and you want to use more standard units, so we use watt hours. So what I'm going to do is divide 720,000 joules by 3,600 joules, and that ratio is going to give us the watt hours. So when you divide that out, you end up getting 200, and that should be watt hours. But to make it more correct, because the units, I know that you don't see the units being displayed correctly here, so what I'm going to do is, let's see, if I put in, divide this out here, have 1 joule here, let's see, I can take another method here to kind of do it in that way, and is to go back to this and multiply both sides by the number of hours, and let's see if that's gonna work right. I can just use this equation and say the power, which is 100 watts, times the hours, which is 2 hours, and that is 200 watt hours, which we have here. And just to do a quick check, 200 watt hours, so you have 1 watt is 1 joule per second, 1 hour is 3600 seconds, and I should end up with what I had up there. To check it, let's see, 2000 times 3600, and I get 720,000 like I had up there. Seconds cancel out, and I get joules. So that is the total amount of energy consumed. Or I can say, for example, let's see, that is 5 places. I could say 720 kilojoules. But if they ask for watt hours, you could have simply used this equation and put in the number of hours multiplied by the power, and that would be it. I'll see you guys in the next video.